So, good morning everyone. So, my name is Anandan, service engineer from Metrom India. Okay. So, Metrom is one of the global analytical instrument company. They are involving in different departments actually. So, spectroscopy, titration, electrochemistry, ion chromatography. They are fabricating different instruments, analytical instruments. So, this is one of the Metrom product. So, this is an electrochemical instrument actually. Okay. So, nowadays many of the analysis requires a electrochemical process. Okay. Electrochemical analysis. Okay. So, like whatever we are doing, suppose if you want to characterize any material or analyze a material, so we need electrochemical equipment. So, this is one of the electrochemical equipment from Metrom brand. Okay. So, today we are going to cover EIS. Hope you heard about the EIS, or if you are new to EIS, no issues, we will start from the scratch. Okay. So, I hope this session should be the brief and more crisp. Okay. So, without wasting any time. Okay. So, first of all, okay. So, first of all, EIS is a electrochemical impedance spectroscopy. Okay. So, this is what is EIS means. Actually, this is also resistance only, but in EIS additionally reactance will involve. Okay. So, in generally DC, AC, two things is there. So, okay, hope you are aware of DC and AC currents. Okay. So, when we going to DC, we call it as resistance, but when we come to AC, we call it as impedance. But in both the cases, we are talking about the resistance only, but particularly in DC, we are calling it resistance. In AC, we are calling it impedance. Why means in AC, additionally one more factor has introduced in AC, because AC is alternating current, because current is flowing alternatively, each second current direction is changing. So, because of this, a new factor has introduced called reactance. Okay. So, resistance you may aware of that, because resistance is very easy, but reactance, maybe some of you, maybe this is the first time you are hearing this word reactance. So, reactance is a combination of capacitance and inductance. Okay. So, resistance we know everyone, okay, everything, because we are learning from our school days itself, we are learning what is resistance. Okay. But we are going to know what is reactance. Okay. So, reactance is a combination of capacitance, inductance. Okay. So, capacitance, any idea? So, it's just no issues, whatever you know, you just tell me, we are just learning only. Okay. So, capacitance, what is capacitance? I think somebody from this side has started, right? Capacitance is simply a charge storage device, that's it. Okay. Then what is inductance? So, capacitance we know it is a charge storing devices. Then what is inductance? Charge? Yes sir.
Dispersing.
Sir?
Charge dispersing device.
Actually, for more clear, that is inductance also, it's a energy storing device only. Okay. But both capacitance, inductance, both are energy storing devices, but particularly in what way they are storing the charges. See, that means saving the energy is very important. That means in capacitance, storing the energy in the form of charges. In inductance, storing the energy in the form of magnetic field. Okay, we saw that in pictures, we saw that waves like that, right? So, that is magnetic field. So, both are very important. This combination of these two elements behavior is called reactance. So, capacitance and inductance. So, generally impedance is resistance plus reactance. So, resistance plus reactance. Okay. Generally it is opposing a current. In DC, if current is opposing means that is resistance. In AC, the current is opposing means that is impedance. Impedance or reactance? Impedance is combination of resistance plus reactance. Reactance can't alone, it's not opposing. It's a combination of, that means reactance plus resistance is impedance. Clear, right? So, this is the basic definition of impedance. When we talk about the impedance, it's a simply opposing the current, but additionally not only resistance, in combination of reactance. So reactance is a combination of capacitance and the inductance. So capacitance is a charge storing device storing energy in the form of charges, inductance storing energy in the form of magnetic field. Clear, right? Okay. So when we comes into electrochemistry, so two techniques is very, very important. What application you are working, whatever that means, you are working on that means supercapacitors, batteries, energy related devices, corrosion, like sensors, OER, HER, what kind of applications, even a photovoltaic solar research, CV and impedance is very, very important. This is very two techniques is basic for electrochemical studies. Okay. Okay, CV is that one more session is there for covering the CV. So in this completely we are talking about EIS. So in EIS, this is one of the very, very important technique actually. So comparatively, if you take any other technique like CV, LSV, whatever the DC techniques, that is a destructive technique. That means if we are testing our sample, your sample must get destructive actually. That means we are applying input, we are polarizing the material, your material will get disturbed, but in EIS it won't disturb much actually. Okay, but still we can measure, that means whatever the actual characterize or actual properties of the material, that we can observe without destructing the sample. This is the advantage of EIS. Okay, so this is important technique. So generally for non-destructive, this is a non-destructive method. So without destruct, for generally corrosion people, first they are doing the EIS. That means once they polarize, your material will get, it will be disturbed. So without disturbing the material, EIS is the one of the best technique to analyze the properties of our sample. Okay. So in EIS, simply we are applying, we need to apply some input, right? To get the output, we need to apply some input. So what we are going to apply? So that is, here we are applying a pure sine wave. Okay. Here simply we are applying frequency, that is our input. Okay. In other technique like CV is there, either we are applying voltage or current, whatever in other techniques. But in EIS, generally simply we are applying sine wave, frequency only. So from high frequency to low frequency, we are going to sweep from high to low. Okay. In this frequency, we will get a complete behavior of our sample. Okay. So if you run a EIS, you will get a data that is just a data only, that is not a direct result. So once you get the data, you have to interpret. Okay, that interpretation is very, very important here. It's not like other analytical instrument, like we are getting the direct results in ppm, impedance, not like that. So only we will get the data. After that, we have to analyze the data. That means interpret the data. That interpretation is very, very important. Okay. So this is the basic information for EIS. So what input we are applying? Current or voltage? Okay. Still some people are still confusing. Clear, right? So frequency only we are applying. Right. Pure sine wave. Okay. Then what are the parameters we can observe or we can find out from this EIS? This is very important. So we are going to run we have right now we are having a sample. So what are the output we can get from the sample, or what are the parameters we can get from we can analyze from the sample? Okay. So so first thing is internal resistance or solution resistance, right? So every material has its own internal resistance. So that resistance we can find out using impedance. Then charge transfer resistance. So both are resistance. So anyone can tell us what is internal resistance and charge transfer resistance? Any idea? Okay, anyway, so internal resistance you know, right? So that is by default your sample has some minimum resistance or solution resistance, that is internal resistance. So charge transfer resistance is, so if you are applying some input to your material, your sample, whatever the input, either current, voltage or frequency, whatever the input, so your material has some minimum resistance to oppose our input. So every material has resistance, right? So we are trying to disturb the material. So every material, at least some minimum level, it try to oppose our input. That is because every metal has its capacity, right? So that resistance is charge transfer resistance. So first one is internal resistance. That resistance is resistance at idle. We are not disturbing the sample. By default, that resistance has generated. That is solution resistance or internal resistance. But this resistance is while disturbing your material, at least will try to oppose some minimum level of our input. That is charge transfer. This is the actual ability resistance of your sample. This is charge transfer resistance. So internal resistance and charge transfer resistance, right? Third one is double layer capacitance. Okay, you may hear about CDL or DL, double layer capacitance. Okay, so this double layer capacitor is, so some material having the capacity to, suppose if we are applying the input to your sample. Okay, so instead of transferring the charges, because if it is a conductor, whatever we are applying, it has to transfer, right? But some materials act like a capacitor. Okay, so that in some samples may by original nature is a capacitor. In most of the sample, the nature is double layer capacitor. This is not like an exact capacitor. So what is capacitor? Just I think just 5 minutes back only we have discussed it. In form of, okay, in form of charges, that is capacitor. Then what is double layer capacitor means? We are testing our cell, right? Okay, we have a sample, we are dipping in the solution and we are running the EIS, right? So once we dipped in the solution, what is the in solution, ions will be there, right? Okay, so your material has some charge. It's not electron or ion. Everything has different meaning. Charge, electrons, ions, it's completely different. I think you should not confuse with all of this. Okay, so if I am dipping my sample in the solution, it has some positives. Just let's say it has positive charges. Okay, then what will happen? Once you dip your positive charged material in the solution, what will happen? Negative charge will attract. Exactly. So negative charge will attract, right? So the negative charges will completely absorb. That means absorption. It simply surrounded your material. Then what will happen? The rest of the ions still there in the cell. Still many of the ions are there, but it cannot directly get in contact with your your sample. Why? Already negative charges are accumulated. So it simply hinders the rest of the ion to your sample. So this is also a capacitor, right? Capacitor is simply charge storing device. That means charges are accumulated on the surface. So here also your ions are accumulated on the electrode. So this simply hinders. That means charges are stored. So then it is also like a capacitor, right? So this is called double layer capacitor. Hope you clear the right? Are you clear or some doubts? Suppose if you have any doubts, you just tell me. You just stop me right there. We will discuss and then we will move on. Okay. So I hope you understand the double layer capacitance. Okay. That means your material may not be a capacitor, but once get in contact with the solution, it may act as a capacitor. That is not a actual capacitor. That is a double layer capacitor. Okay, clear, right? So what are the 3 parameters we have covered? Double layer resistance. Who told double layer resistance? Okay, no issues. Okay, so we are just learning. Whatever you know, you just tell me. No, you just tell us. We are just discussing only. Okay, I am not examining you. Whatever you know, just I'm not. It's not like that. Okay, so internal charge transfer, then double layer capacitor. So another one is Warburg. Warburg impedance. The name is WARBURG. Warburg. Okay. So Warburg is simply denoting the diffusion properties of our sample. Okay. So diffusion. What is diffusion? What? Yes, sir. Definitely, ion moving is diffusion, right? But in always ions will move. Otherwise, if you that means if there is a difference, definitely ions will move. But what is diffusion? What, sir? Actually, thing is, diffusion is also just like ions is moving. That is correct only. So diffusion is so usually in diffusion also, as you said, ion will move, but ion will always move or it will stop at certain position. Okay, that means for example, diffusion is simply depends upon the concentration. Okay, so diffusion. So if there is, suppose you are having the water, that means some solution. Okay, constant, that means conductive solution. You are having some in the other hand you are having that concentrated solution in this diluted solution. If you are adding a small amount, it will slowly, that means here the diluted concentration is more, that means what are the solution, in that solution the dilution is more. If you are adding a small amount of concentration, it will slowly diffuse. But if you add more amount of concentration, the diffusion rate will be more. Okay, so the diffusion is simply that means your ion is getting dispersed throughout the solution, your ions is moving. So the concentration of ion, that means the concentration of the solution decides the diffusion speed. Okay, so simply diffusion is ion movements, right? Okay, so ion movements. So this diffusion properties we can observe using the EIS. So that is called Warburg impedance. Okay, because because if you take any sample, electrolyte will be there, because that electrolyte is the responsible for conduction. Okay, so that diffusion properties we can observe, because diffusion, based on the diffusion only decides the conductivity rate, right? So that diffusion properties we can analyze through the EIS. Sir, actually it's about the cell. It's not, yes. Your sample also involving.
Cathode to anode, how it will be
Yes, sir.
ions.
Yes, it's simply concentration gradient. If concentration is more, your diffusion will be more. If concentration is less, your diffusion will be less. Okay? Yes, sir.
Two types, single layered capacitors and double layered capacitors. And what about single layer capacitors?
No single layer capacitor, sir. It's only double layer capacitor. Actually, capacitor is just like a charge storage. Okay. But in double layer capacitors, particularly only happens in sample machine, particularly in cell. Once you dip your charged material in the sample, in this electrolyte, ions are get attracted to the electrode. So that time only double layer will form. Okay, this is not like a capacitor. It's a double layer. There is no single layer capacitor, only double layer. Okay.
The double layer maybe is the electrode potential, known as also electrode potential.
What, sir?
The double layer is also known as electrode potential.
No, no, sir. Electrode potential. Electrode means reference potential. Are you asking for?
When the metals is dipped in electrolyte,
Ah.
the charge surface will form.
So can I explain?
Yes, sir.
Actually, in a double layer, this thing is, suppose you just imagine your electrode having some charges. For example, assume it's positive charge. So, and your electrolyte having positive and negative charges. Okay. So, if a positive charge in an electrode, we are going to dip it in an electrolyte, then automatically all negative charge will come and accumulate there. So, one capacitor means is needed two electrode. One is a positive electrode, one is negative electrode. So, then you assume that your electrode which you are dipping is a positive, and the accumulated all negative ions will form a artificial or imaginary one electrode there. Okay. Then you imagine in the electrolyte having the other positive electrode also, positive ions also, not electrode, positive ions also. So if there will be accumulation of negative ions, automatically positive ion will be accumulated at the other side. So then you can understand that one electrode, center one single electrode, that's called the negative potential what is accumulated. Then inner there will be a positive electrode of the original electrode of the material we are dipping, and another artificial one is created outer. So total there is a two capacitors connected series. So that's why it's called a double layer capacitor. Okay.
Okay. It's clear, right? Actually, That's it. Whatever he said. That for if you want, that means if you want to know more about the double layer capacitor, simply it's working based on Helmholtz double layer. Okay, so you may heard about that. So this is the actual function. Okay, so Helmholtz double layer is the actual name actually for this. You can learn about the Helmholtz double layer. Okay, so this is just a beginning session, right? So we cannot get much into this. So, okay, so because of that, so we are just covering it just like in brief session. Okay. Okay, so whatever you know, that means whatever you wanted to know, you just tell me. If it is not possible in this session, I will just tell you the hints. You can refer that, and then based on that, you can learn more than that. Okay. So, okay, what is the last one we have talking about? We were talking about Warburg. So, what it is denoting? Okay, so diffusion, right? So, what are the four things we have covered? Okay, what is the another name for internal resistance? We have solution resistance. Okay, so these are the, if you take any sample, these are the four major characters of our sample. So if you are analyzing the character of these samples, that would be very useful to define our sample. Okay, so clear, right? So we have, so these are the thing, theoretically these are the things what we are going to see in this session. Okay, so right now, any doubts in this thing? Because whatever we are talking about, we are going to see, we are having on sample, we are going to see this. Okay. Okay, sir. So what input we are going to apply to our sample? If, okay. What input we are going to apply? Sine wave frequency. Frequency. Which is correct? Sine wave frequency or frequency? Okay. Then just tell me, if you know things, you can tell me what is sine wave and what is frequency. If you know, you can tell me. In the meantime, I will open the software and I will arrange the things.
We are applying, so that is should be sine wave, and what is actually frequency is actually the reciprocal of the wavelength of that side.
Okay, clear? Can any you got so got it right? Can you tell me? Okay. So for more clear, I will tell you, sine wave is just a sine wave. Okay, frequency is number of cycles per second. Okay, number of cycles per second is frequency. So in second, how many sine wave is going? That is frequency. So sine wave and frequency is not the same. Okay, so now you just tell me what we are going to apply, sine wave or frequency. Then we are not going to apply frequency. We are applying frequency or sine wave? Frequency, right? Okay, so don't forget, sine wave just a normal wave, single wave. Amount of, that means how many waves is crossing per second is called frequency. Number of cycles per second is frequency. Okay. So now this is the electrochemical workstation, as I said earlier. This has a EIS measuring range of 1 megahertz to 10 microhertz. So each instrument having different measuring ranges. Okay. So high frequency. So we are going to sweep a frequency. So we know that we are going to apply a frequency as an input, but actually we are sweeping from high frequency to low frequency. We are going to sweep. Okay. So in each frequency, the data will be recorded. Okay. So that we are going to analyze, right? So 1 megahertz to 10 microhertz, sir. Okay. So here, so this is impedance spectroscopy technique. This is the software is Nova software. This is impedance spectroscopy. Here you can see impedance, FRA impedance potentiostatic. Okay. So this is the date. So this software as a default technique. Okay, no need to modify much actually. It's almost a optimized technique. Okay, so now, so this is one of the simulator, like what it will simulate the exact sample. So as of now we don't have any sample. So to simulate the exact sample condition, we are having this cell. So this will simulate the exact sample conditions. Okay, so first let me connect.
I will give a little more explanation on this.
Yes sir.
Called demo cell. Okay. Any electrochemical cells like a solar cell or supercapacitor,
Need
whatever
mic
you
sir.
are fabricating can be converted or can be make it as an electronic circuit like a capacitor, resistance and impedance. Okay. So whenever you are going to fabricate or if you are going to do a research on solar cells, when you are going to publish any new cell or new combination of cells, definitely they will all journals will ask what will be equivalent circuit of that your cell. Okay, so that normally will understand through this EAS analysis. Okay, so this cell is actually simply electronics device, but it's having a combination of capacitor, resistance and impedance, and then that combination will say one combination of port will be act as a solar cell, another combination is act as a supercapacitor. So for them easiness, actually they are making this demo cell for explaining the whole techniques what we can do with this thing. Okay, that's all. You just imagine his connection going to be a either it will be a supercapacitor or maybe a corrosion testing unit or maybe a solar cells. All electrochemical things we can make equivalent circuit. That equivalent circuit will be actually this.
Okay. Okay sir. So so just leave the connections, because connections is varying to different instruments, to instrument it will vary. So first we will just first we will just take a look of the graph, then we will just analyze what are the parameters we are able to get, then we will analyze. Then one more thing, as I said earlier, so this is just a data we have to interpret, then only that exact results will we can get. Okay, so for that, so 1 e power 5 means what? 1 e power 5 means 100 kilohertz, 100 kilo. Okay, so here we are applying a frequency, right? So high frequency to low frequency we are going to apply. Okay, so first frequency is, so we are going to sweep from 100 kilohertz to 0.1 hertz. Okay, so this is the 1 e power 5 is 100 kilohertz. So last frequency is 0.1 hertz. Okay, 0.1 hertz means how many millihertz? Yes, 0.1 is 100 millihertz. Okay, so this conversion you should know, because in many of the instrument mostly it is in decimal forms only. You have to, there is no direct unit. So if it is like hertz means, if I want to apply 10 microhertz means you have to put it 0.0001 like this. This kind of decimal forms you have to remember, because most of the instrument having this decimal forms only. Okay, so we are going to sweep from 100 kilohertz to 0.1 hertz. That's it. This is sine wave or frequency? Frequency. Okay, so let's start. So why we are recording from 100 kilohertz to 0.1 hertz? Why we are sweeping first of all? Why don't be a single frequency? Any idea? Because as I said earlier, because we have multiple parameters, so it's not a single parameter, we have multiple parameters. So in each frequency region, because all the parameters we can't get in single region. So in each region we will get different parameters. So that's why we are sweeping from high range to low range. Okay. So usually resistance will capture at high end, capacitance will capture at low end. Okay, so for the because of this only we are sweeping from high frequency to low frequency. Okay.
Another practical application is if you are using a fabricating a solar cell, our input source is actually the sunlight. Sunlight is actually not a single frequency, it's a group of frequencies. So that we have to accept this all multiple inputs. So that's another reason for you are testing your device in a large range of frequencies. Okay.
Okay. So simply we are applying the 100 kilohertz to 0.1 hertz. Okay, we are getting the data. Okay, so in this only whatever we have discussed, right, that 4 parameters, all the parameters will be in this graph only. Okay, so we have to interpret, then analyze, we have to get the extract the data. Okay. Okay, so we have two graphs here. So the first one is Nyquist plot. Okay, the first graph is Nyquist plot, second graph is Bode plot. For generally, Nyquist is sufficient for most of the analysis. Okay, for very few applications only Bode is required. So what are the two plots name? Nyquist, Bode, right? BODE, Bode. Okay, so Nyquist and Bode. Okay. Clear, right? So it is still running. So you can see, so it is running. It is not completed yet. It is still running. So once it's completed, we will just open the graph and then we will analyze this. So now that loading symbol has gone. So now it is completed. So this is the graph. Okay, this is the typical impedance graph actually. Okay, so in this we have internal resistance, charge transfer, double layer. Warburg is there or not? Some if anyone having already experience with EIS, they can tell EIS is not or present. Okay, but no issues. I think it seems like many of you are new to this impedance, right? Okay, so by seeing the graph, once you get experience, once you used to it, so by seeing the graph itself, we can easily tell what are the elements present inside. That means what are the parameters available in this graph to extract, right? So generally, once you get, this is a typical semicircle. Whenever you are having in your sample having that double layer capacitance, this kind of graph will come. That means whenever you are having, definitely solution resistance will be there. That is internal resistance, because without that nothing will be there. Solution resistance will be there. And if you are having double layer capacitor means, that means the double layer capacitance is more means you will get a proper semicircle. See, it's like a proper semicircle. Okay. If the capacitance is less means you will get a suppressed semicircle. Okay, it will come like this. The starting and end point will be the same, but the height of the semicircle will be suppressed. That is if you are having less capacitance. Okay. So if you are having more capacitance, what will happen? Any idea? If it is less, it will suppress. If it is more, what happen? Full? It is also full semicircle. Any other? So it's a full semicircle only. Okay, it's a complete semicircle. If your capacitance is, that means if you are having a good capacitance, double layer capacitance, your graph will comes like a complete semicircle. If it is a capacitance is less means you will get a suppressed semicircle. So I am just asking, in contrast, instead of suppressed, that means instead of lesser capacitance, instead of lesser, if you are having more capacitance, what will happen? It's just like just a guess only. It's not necessary to know, because you are the first time you are hearing, right? Just tell me, anything is what? Already you have seen some, okay. So it's simply like if your capacitance is more means your semicircle will start to float. It will not complete. Okay. If capacitance more, it will stop here. It will stop here. If you still capacitance is still going means at last you will get a straight line. So the amount of simply the height denotes the capacitance, that means amount of capacitance, right? If it is more, initially if capacitance more, your semicircle will not be a complete. If it is more, simply it started slowly into a convert, that means it slowly turns into semicircle into a straight line. That is a, if you are having more or less, more, right? So that is, so internal resist, that is double layer. So the wherever in simply in Nyquist plot, this is the Nyquist plot, wherever the EAS graph starts, that point denotes the internal resistance or solution resistance. Okay. So now can you tell me what is the resistance? Solution resistance or internal resistance? Just tell me, no issues, whatever, if it is right or wrong, you please tell me. So the I clearly told you, wherever the graph starts, that points denotes internal resistance or solution resistance. So now you just look at the graph where it is starting exactly, 100. So your solution resistance is 100. Okay. Okay. So solution resistance, then double layer. So what is double layer, we have seen, right? So that amount of, that means height of the semicircles directly representing the amount of, that means amount of capacitance. If it is less, suppressed; if it is more, slowly it will turn into a straight line. Okay. Then one more thing. So wherever the semicircle ends, it's not a graph end, it's a semicircle end. So wherever the semicircle end, that is charge transfer resistance. Okay. So what's the difference between solution resistance and charge transfer resistance? Yes, yes, tell me.
Starting point, the graph is internal resistance,
Hmm.
and after ending the semicircle point is charge transfer resistance.
Okay. Is that correct or wrong? You are tell what I'm asking. I was asking, what is the difference between internal resistance and charge transfer resistance? Okay. You are telling what is internal resistance and what is charge transfer resistance. Yes. Simply both are resistance, right? I am just asking what is the behavior of this resistance, what is the behavior of this resistance. This is
Presence inside the sample is
what?
internal resistance.
What, sir?
The sample resistance presence inside the sample is internal resistance.
Okay. Inside the sample. What? With input, without input. Okay.
So after the input, the sample will have more resistance.
Okay, so very good, clear actually. So simply your material is not active, that is idle actually. We are not giving any input to our sample. That time the resistance is by default it is generating. That resistance is internal or solution. It's a combination of a cell. Okay, not only your sample, because it's a cell, complete cell. Okay, including your solution resistance, sample resistance, everything. But in charge transfer resistance, that is denoting exactly your sample resistance. That there only we are disturbing some, we are giving some input, it will get disturbed. That time it will try to limit our input. Okay, try to oppose our input. That time resistance is created. That is called charge transfer resistance. Okay, so charge transfer, double layer, charge transfer, double layer. Okay, no issues. Okay, charge internal resistance, double layer, charge transfer. So wherever the graph starts, that is charge transfer or double layer. Okay, so middle one is, that means the height of the semicircle is representing double layer, and end of the semicircle is. So what are the, still one more parameter is there. What it is denoting? Okay, so still that one is pending. Okay, actually in this test cell we don't have option to simulate the diffusion properties, but I will tell you we have one more data here. In that I will explain how the diffusion graph will be. Okay. Okay. So generally after the semicircle, whenever you are getting a 45-degree line, that's simply denoting Warburg. Warburg or diffusion. Okay. So Warburg is the name actually. Diffusion is a property. Okay. So Warburg, right? So I will tell you, I will show you. So in this, so here also you can see, so here also you can see a semicircle is there, and after the semicircle what is happening here? One straight, it's a straight line or what?
Not straight line.
It is a straight line or what? The line is straight or flat or diagonal or perpendicular, what? Okay, but you just you know that, but the same semicircle here also is there. So internal resistance, charge transfer, double layer. So after the semicircle, whenever you are getting this 45-degree line, so this is very important. This 45-degree line denotes the denotes the diffusion property. The name is Warburg impedance. Okay, so this Warburg that means this diffusion simply describes your electrolyte ions properties. Okay, because this electrolyte because electrolyte only having this ions, right? So this electrolyte decides the conductivity, movement of ions, everything. So this diffusion property clearly describes that. This Warburg clearly describes the diffusion properties. So whenever you are getting a 45-degree line after the semicircle, you will get a diffusion. That means it is once you see the graph, it's very clear, right? So whenever you are getting 45-degree, diffusion properties is there. Okay. So this 45 degrees line is, it's not exactly, it's 45, approximately 45-degree line. So this degree of line is also indicating different things. So instead of 45-degree, if I am getting 90-degree means what will happen? What's happening there? So you have answered like if it is, that means capacitance is less, suppressed semicircle will come. So like this is also, if you are getting a 45-degree line, it is, that means that your diffusion properties is there. That means it's like a electrolyte diffusion properties. It's a very good diffusion properties. If it is a 45, instead of 45-degree, line is shifting to like 60, 70, 80, 90 means what's happening? Diffusion is increasing or decreasing? Your ion properties, that means ion diffusion is increasing or decreasing? Decreasing or increasing? Decreasing. So how many of you agree with her? Decreasing, sir? Increasing. So decreasing, increasing. Increasing. So you are also increasing. What, ma'am? Increasing. So almost I think it seems like many of people are agree with the increasing. Okay? That is exactly wrong. Okay? Thing is, so whenever you are getting, anyway it's not necessary, you are just guessing, right? Okay? So that is whenever that means this 45 degrees shifting means your diffusion property is getting less actually. Okay? So whenever you are getting proper 90-degree line, it acts as a capacitor. Okay? So capacitor won't allow the charges to move. That means won't allow the ions to move. Okay? So that means it acts like a capacitor. So when instead of 45 degree you are getting 90 degree, it simply denotes the diffusion is decreasing. That means they are also here that capacitance is yes, capacitance is there. Okay, so this is what the diffusion properties. Okay, so whenever you are getting 45 degrees, diffusion is increased. Diffusion is there, proper diffusion properties, and if it is decreasing, or that means your line is shifting. Whenever you are getting 90, that means it is closely approaching a 90, means your diffusion is less actually. Okay. Okay, so this is how we need to interpret the data. So by C, but still we didn't get any values. We simply know this is internal resistance, charge transfer, double layer, and some Warburg is there. Okay, yes, diffusion is there. Okay, but we need a value, right? This much of resistance, like 100 ohms, 200 ohms, 300 ohms resistance. This microfarad, this farad, this capacitance, this much of defined capacitance has to we need to find out, right? Okay, so for that we need to do the circuit fittings. Okay, so we are going to draw a equivalent circuit. Okay, that means we are going to draw a circuit which should be exactly equal to this. That means equivalent circuit. Okay, so once you made the equivalent circuit, we will get a values on the circuit itself. So that circuit clearly tells you how much of resistance, internal resistance is there, how much of charge transfer is there, how much of diffuse, that means the capacitance is there. Like that it will tell you. Okay, so hereafter we are going to fit a circuit. So let me go to the first one. This is very easy to understand. Then we can, so once we understood the basic concept, means that would be very useful for you, because this is just a basics only. So based on this only, if you approach many datas, you will get more knowledge on circuit fittings and EIS datas. Okay. So first one is you first observe this, then we will discuss, right? So in this software, fitting is very easy. Just you first observe this. So this is my graph. I want to make a 3 points in this graph. Based on that, software will automatically draw a circuit. Okay. So I am going to make the first point here, and second point here, and third point here. Anyone can tell me why we are selecting these 3 points? What?
Initial point represented
Okay.
ending of the semicircle charge transfer.
Okay.
The middle one is double.
So we need to make a 3 points. Okay. So we are simply just start, end, and middle of the semicircle. Okay, because each point is denoting some parameters, right? Okay, but minimum 3 points is required. Okay, but more than 3 also you can give, if it is not properly overlapping with your actual data. You can add more data points. So we have drawn this pattern. Okay, then in right side you can see results. I am just copy the value. Okay, then just go back, fit and simulation, go to edit, just paste. So once I pasted, automatically circuit has created. So after that I have to click OK. So now you can see, so this dotted points is our actual data. So that line is the fitted data. So if both datas are overlapping, our fitting is right. Okay. So simply this is also just, it's not like every fitting is correct. So we have to check. So first of all, it should properly overlap. Our theoretical and our raw data and our fitted data has to properly overlap. If it is properly overlaps, this is correct. Then fit and simulation. So now you can see the value. So what is our internal resistance? Okay, actually here I have connected in this circuit, right? So the value in this circuit has to come here. Okay. So here my internal resistances, you can see I am connecting in this point. This is 100. So this point is 100. So this is internal resistance. And so here you can see is, let me for more clear. So here you can see is, then you come to here. So I am connecting this point here. So resistance is 1 kilo ohms. 1 kilo ohms means 1000 ohms. Okay, so 1 kilo ohms means 1000 ohms. So here we are getting 978 ohms. So the resistance slightly it's oscillating, right? This is not a precision resistor. So it's a dummy cell resistor. Okay, so resistance. So another, what is the capacitance is 974. What is that NF? Microfarad. NF. Okay, so 974 nanofarad. Okay, so here what is mentioned? 1 microfarad means for out of 1000 nano 974 nano, because these are this old dummy cells and just for demo purpose only we have brought this. So this is a old, some slight variations will come. So if you like this, see exact whatever is there, the exact value it can simply extract. So like this, if you are doing EIS test, the actual data, exact data will come without disturbing your sample. Okay, that's why EIS is preferred over other techniques. Okay, so this is how so now I just copied the value and I pasted here, automatically it draws a circuit. Do you know why this is why the first, what is the first one? How can you say why this is internal resistance? What?
The range we can see.
That means you are telling that value 100 ohms is there. That means here that 100 ohm internal resistance is there, here also 100 is there. So you are simply matching. But
Our starting point we got the graphics.
yes, that is yes. That's what I am asking. In our graph, the first point is 100. That is internal resistance. But in this circuit, how can you say this is the internal circuit, the internal resistance? What, sir? Units, sir. Which units? We have both resistance. Here also resistance. Here also resistance. Here also resistance. We have two resistance, right? Internal and charge transfer. I am just asking which one is charge transfer and which one is solution or internal.
First one is internal resistance. The second one is charge transfer.
Is that correct?
We have studied the EAS right now. So this is EAS equivalent circuit. So EAS is a combination of resistance and reactance. Right? Reactance is a combination of capacitance and resistance. Okay, understood. So inner resistance is purely resistance, and the other part is actually a combination of capacitance and resistance. That's why we can separate like this. Okay, first part is the resistance alone. That's the internal resistance or the natural resistance of the material. Other part is actually the charge transfer, which include the capacitance part as well as impedance part. Am I right, sir?
Yes, sir. Almost, sir. So actually, how many of you heard about apart from internal and charge transfer, RS and RP, series resistance and parallel resistance? Series resistance and parallel resistance. Heard about this or series resistance and parallel resistance? Apart from internal and charge transfer, series and parallel. Heard about it, right? Okay. Then what is series resistance? What is parallel resistance? It's completely different from internal resistance and charge transfer, or both are same? So here you can see RS. RS means series. Here RP, parallel. So RS, RP is there. So internal and charge transfer is also there. So totally we have 4 resistance or only 2. So you are clear in this. So only 2 resistance. So internal resistance is also called as then okay. So why it is so why so you are clear. So internal is also called as and RCT. RCT or charge transfer. So RCT is not a parallel resistance. RCT. So she is telling RCT and charge transfer both are simply charge transfer. That's what I am RCT. Okay, don't get confused. Okay, okay. So RSRP. So charge transfer internal resistance. Should not confuse with this. Okay. So thing is, so so there is a pattern. We should not. We cannot directly like we can put all the elements in one after another. Okay. So there is a strong concept behind this. Why we are making a circuit in series and parallel. We should know this, then only we can make a circuit. After defining the circuit, then only we can get the exact values. Getting data is very easy. We can simply connect the sample and simply one run button. That's it. After getting the data, we have to interpretation is what? We have to create an equivalent circuit. Then only we can get the exact values. Right? So without developing the circuit, without drawing the equivalent circuit, we won't get any values. Okay. So for that, we need to know draw a circuit, how to draw a circuit. Okay. So for here, first we have just inserted the, let me delete this. So here, what is my first resistance in my graph? Series resistance or internal resistance? Okay. So, okay. So add element. So first graph, first element is internal resistance, right? So there is no separate resistance. We are in particular area we are calling it internal resistance. In other area we are calling it charge. But resistance is here we have only one element resistance. Okay. So first one. So then second one is what? That is charge transfer, and remaining one is double layer. Okay. So in this you just watch this, add connection. I am going to draw either both, that means capacitor and resistor in parallel. Why I am going to draw in parallel? Because I added resistance in series, first one, because we got the internal resistance initially, so we added the resistance. Then why should I add a resistance and capacitance in parallel? Okay. Okay. So usually what will happen, if I apply some input to your material, what will happen? Your material what will do? What? Initially at the very beginning, once you give the input, what will happen? Okay. So clear, ma'am. Good. Okay. Oppose the electrode. Sorry, oppose the our input. Okay. So if I am applying current, okay. So it is opposing. Opposing means it is not letting ions to transfer. It is simply stopping the flow of ions. That means once it stopped means it cannot move, unable to move anywhere. So it simply what will happen? If it is not moving means what will happen? We are applying our input, that means current or voltage, whatever, to your sample. Just consider say electrode, to your electrode. So our electrode is simply opposing. That times ions won't move other side. So it's simply what will happen? It will come back to the instrument. Then what? But my question is clear, right? So we are applying some input. Your material is opposing. Then what will happen? That means your input, your current won't move. Then what will happen there, particularly there? Electron? Yes, that's what I am telling. It cannot transfer because Your material is opposing our input. Then what will happen? What? No, sir. That's what I am telling. Here, for more clear, we are still applying our input. There is no way to come back on the same way. There is no way to come back, first of all.
Store the charge.
Yes, this is what we have discussed about capacitance. We are applying input, it simply holds the charges. It won't allow the charge to move. That's why capacitance is built. That's why capacitor is working. So here also, I am applying some input to your material. It is opposing. Because of opposition, your ions won't move. It is simply stores, that means gathers around on your electrode. Okay? Then what will happen? It simply stores means what will happen? What will build? Exactly. So double layer. So capacitance is building. So resistance is created. At the same time, parallelly, capacitance is also building. So you observe this, both are happening parallelly, simultaneously, whatever. So that's why we are make the circuit in parallel. So resistance and capacitance both are happening simultaneously. So that's why we are making the parallel circuit. So resistance and capacitance. Okay. So go to add elements, resistor. Is it any problem? That means if I put the resistor at the bottom and I put the capacitor on top, any fixed point is there, or just your view? I am just asking. We know we have to put it in parallel. Either resistor should be in top or capacitor should be in top. Why? Actually, it's nothing. It's simply in parallel. Both are happening simultaneously. It's parallel. Which one? Anyone can be in top, anyone can be at the bottom. Okay. So I am just adding the resistor and capacitance. Clear, right? So in this graph, that's it. Internal resistance, charge transfer, double layer. Okay. So I am going to close the circuit. So add connection, parallel join. Okay. I just closed. So these are the default values. Okay. Once you click OK, it will get the actual value from the graph. So first let me give OK. Then if you go there, you can see internal resistance, charge transfer and capacitor. So this is how you need to create a circuit. Okay. Now you try to fit the Warburg. So first let me. Okay. So what we have to do for fitting, for creating a circuit, what is the first step? Yes, we should select the point. Which point we should select? Starting. End means this end, right? She's telling us. How many of you? That means. Clearly remember, it's not a graph end. It's a semicircle end. Okay. So semicircle end, and another one is. Yes, double A, middle one, right? Okay. So now you can see some line has drawn actually. I told you, right, for more proper overlapping, you can add many points. So you can see it is shifting, that line is shifting, right? Okay. So that's it. We can only make a point to semicircle. If anything is there, that element we have to add in that circuit section only. Here we cannot do anything. Okay. So as of now we marked 3 just points actually. Then copy the value. So once we made the points, automatically in result section the values will come. So we have to copy the value and go to effect and simulation. So this is called circuit description. In circuit description only we have to create a circuits. So here what we have to do? So control V. So here you can see what's happening here. So here if I give without Warburg, what will happen? I am just giving okay. So now you can see only the semicircle portion has come. So without adding the Warburg, see we have just fixed half of the circuit only, half of the graph only. So that's why we got this result. Okay. So let me add the Warburg. So go to add elements. Here Warburg is there. Just take this. W is Warburg. Just add this and give OK. So now you can see it is properly fixing, right? So thing is, first we should know what are the elements is present. Then only we can add the elements. So for that, by seeing the graph itself, we should know what are the elements present. Then in graph section, we have to add the elements. But only thing is, we should know that why it should be in series, why it should be in parallel. Okay. Okay, sir. So anything else? This is how we need to do. So far we have covered. So theoretical part of EAS and analysis part of EAS also. Okay. So if you have any doubts, the time is over. We cannot do anything. So if you have any doubts, you can just personally you can reach us. We will guide you. Actually, we have discussed about Nyquist plot only. Nyquist plot is more than sufficient for all the analysis. But Bode plot is particularly for phase analysis because capacitance is a phase generative devices. Okay. So for particularly phase measurements, this Bode plot will work. Not for all the applications. Okay, sir. So anything else? Anything you wanted to know or any doubts? Nothing, right? Okay, sir. Okay. Thank you so much. Okay.